I think definitions like static friction is one of those things that people overlook, right? People usually concentrate on Newton's first law, second law, third law, so on and so on. But these kind of definitions are definitions that people oftenly overlook. They don't really give themselves some time to actually go through and memorize these kind of definitions. So I'm expecting that a lot of people actually got 2.1 wrong. But anyway, stories. Let's take a look at 2.2. Draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. Right. 2.2. Just like 2.1. People are not paying attention to the details. So I think that this is another question where people got it wrong. But most people think they got it right, but they actually got it wrong. Let me show you why. So 2.2, the key word here is horizontal, right? We want to draw a free body diagram showing all the horizontal forces. So if you include the vertical forces, I'm assuming you'll probably get it wrong, right? You'll probably lose 1 mark for every vertical force that you include. I think that's probably what's going to happen. So if you include the normal force and the weight, I think you're going to get nothing, or at most 1. But I'm quite sure there's no way you get all the marks if you include the vertical forces. So free body diagram for this object. Let's read through the question statement and see what is happening. In an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table. So already we know that we are supposed to have friction, right? Because it acts horizontal. It is connected to a mesh hanger by means of a light inextensible string passing over a frictionless pulley as shown in the diagram below. Mesh pieces are added to the mesh hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different meshes to increase the hanging mass each time. Ignore the effects of air friction. So right, that is the information we have. And then we're supposed to draw a label free body diagram acting on the crate just before it starts moving. Okay, so obviously we have the tension, right, as a consequence of the light inextensible string that connects the crate and the mesh hanger. And then we also have frictional force, right, acting on the object. So there we go. These are the only 2 forces that we're supposed to have. Frictional force and the tension force. Right, no normal force, no horizontal force. Not because they are not there, not because they do not exist. They still do exist, but the question is saying only the horizontal forces. So we have to respect that. And then 2.3.1. We're supposed to calculate the coefficient of static friction. So we are looking for this coefficient of static friction. So we already know fully well that the static frictional force is equals to the coefficient of the static friction multiplied by the normal force. The coefficient of static is usually greater than the coefficient of kinetic. Right. You will see why I'm mentioning that in this question as we do 2.3.2. So what information do we have? Do we have the frictional force? Maybe. Let's take a look and see what we have here. We are actually not given the frictional force, right? The static frictional force. So how the hell are we supposed to calculate it? But do we have the coefficient? The coefficient is what we're interested in. So obviously we don't have that. What about the normal force? Well, the normal force, we can calculate it, right? Because there's no Fy, the normal force is just going to be equals to the weight. So the normal force, 8.5 multiplied by 9.8. So let me just put this in my calculator and see what happens. My calculator is in scientific, so let me put it back to normal. So we have 83.3 Newton. This is the normal force. And then the coefficient is what we're interested in. So how can we calculate the static frictional force? How can we possibly calculate that? Okay, let's take a look at our scenario here. In 2.2, we have a free body diagram, right, of the crate just before it starts moving. Just before it starts moving, the frictional or the static frictional, it is supposed to be, because it's just before it starts moving, should be equals to the tension, right? But how can we calculate the tension? We are given this diagram here, right? You can see that when the hanging mass is 4.2, our crate starts moving, because that's where we start having a bit of acceleration, right? Right here at 4.2. So the static frictional force is equals to the tension, right? But the tension here on the mesh hanger with the mesh pieces is just equals to the weight, right, of that object. So that is, what is the mass of that thing? Let's take a look. The mass is 4.2 when we start having an acceleration, and acceleration due to gravity is 9.8. So we have 4.2 multiplied by 9.8, which is equals to 41.16. So we have the static frictional force. So now we can see 41.16 is equals to the coefficient multiplied by 83.3. So the coefficient is going to be equals to 41.16 divided by 83.3, which is equals to 0.49. So that is 2.3.1. Let's take a look at 2.3.2. We are looking for the magnitude of the acceleration represented by y on the graph if the coefficient of kinetic friction between the crate and the table is 0.4. So take a look at this. The coefficient of kinetic friction is 0.4, and we calculated the coefficient of static friction to be 0.49. So we are quite convinced that the answer we have in 2.3.1 is correct, because if the coefficient of kinetic friction was greater than this one for static friction, we should be worried, because we know fully well that that should not be the case. So there we go. We have the coefficient of kinetic friction, and then what else do we have? We are looking for the acceleration at y. So we do have the mass, we have the hanging mass, right? So the hanging mass is equals to 7.4. Let's concentrate on the crate. If we concentrate on the crate, F net is equals to ma. We know that fully well. And then the force that is pulling the crate is the tension minus the frictional force that opposes. And this is equals to ma, right? So what is the tension? We don't have the tension at this point. What about the frictional force? We have the coefficient, right? So this is 0.4 multiplied by the normal force, which is 8.5 multiplied by 9.4, 9.8, 83.3. So we have 83.3, and then this is equals to 8.58. So tension minus, so 0.4 multiplied by 83.3, and this is equals to 33.32, and this is equals to 8.58. Okay, so it seems like we are in a we are stuck here. We have the tension, we have the acceleration, and we have two variables, right? So we need another equation. So let's concentrate on the mass hanger. The mass hanger, the free body diagram, it should be the weight and the tension, right? So why is it going down? It is going down because of the weight. So weight minus tension is equals to 8.5, not 8.5a, but the mass of the hanger, which is 7.4, 7.4a. So the weight, 7.4 multiplied by 9.8 minus the tension is equals to 7.4a. Okay. Obviously, in place of tension, we can substitute, we can make the tension the subject of the formula in this equation. So it is going to give us 8.5 acceleration plus 33.32. So instead of having tension there, we can say 7.4 multiplied by 9.8, which is 72.52, minus 8.5a minus 33.32 is equals to 7.48. So minus 8.5 minus 7.4, and that is minus 15.98. This is equals to 72.52 minus 33.32. It is equals to 39.2. But when you take it to the other side, it is going to be minus 39.2. So the acceleration is equals to minus 39.2 divided by 15. Is this 15.9 or 15.19? I forgot what that it is, what I wrote there, because it's not clear. So minus 39.2 divided by minus 8.5 minus 7.4. I can just do that because I'm not sure what I wrote there anymore. So the acceleration that I'm getting is 2.47 meters per second squared. That is the answer to 2.3.2. And here's the question for you, 2.4. A 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the crate? Okay, choose from increases, decreases, or remain the same. Give a reason for your answer. So what is your answer to 2.4? And why are you saying so? Apart from that, let me know which question you want me to do next. Here we go. So I gotta say, I'm quite disappointed because this year there's no free fall or projectile that we need to define. Just like we expect in the previous years, we always had one between free fall and projectile. But anyway, stories, let's take a look. So ball A is thrown vertically upwards at 12 meters per second from the top of the building. 2 seconds after ball A was thrown upwards, ball B is thrown vertically downwards at 5.4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time, T seconds. Ignore the effects of F friction like we always do, and then we're given the position time graph for the two balls. Right, so the first question, 3.1.1, we are supposed to, using equations of motion only, calculate the value of each of the following as shown in the diagrams. And then 3.1.1, we are looking for the time t. So t is the time at which the two balls strike the ground, right? So let me just see the mark allocation. It's 5, so it seems like we might need to do a bit of work there. So if I concentrate on ball A, we have an initial velocity. I always take up as positive, so the initial velocity is going to be 12, which is positive. The acceleration is minus 9.8. And then I'm looking for time t, right? It seems like that is all I have as far as ball A is concerned. That is all I have. So with two variables, I'm not going to be able to calculate the time. I need 3 so that I can pick an equation, and then the unknown will be the fourth. Okay, let me try the second ball, ball B. It is thrown downwards at a velocity of 5.4 meters per second. The acceleration minus 9.8. We are looking for time t. So there we go again. We don't have enough variables, but we have two balls. Can we work simultaneously? Can we use ball A and ball B in order to find our time t? Let's give it a try. So if we focus on ball A first, so which equation do we want to use? We want to use an equation that involves delta y. Why am I using delta y? Why am I choosing to take delta y as the fourth variable? Because they are thrown from the same height. So at time t, when they strike the ground, they have the same displacement, right? So for ball A, delta y is equals to vi delta t plus a half acceleration delta t squared. So vi is 12, time is what we're interested in, plus a half minus 9.8, let's say t squared. So delta y will be equals to 12t minus 4.9 t squared. This is as far as ball A is concerned. What about ball B? When we go to ball B, delta y is going to be equals to minus 5.4 t, right? And then plus a half minus 9.8. I know that he's going to give me minus 4.9, but I'm just choosing to write it as it is because I don't want to go to the answer without substituting because I'll lose marks. Well, I'm not going to lose marks, but if you do it, you lose marks in the exam. But anyway, stories. So ball B was thrown 2 seconds after ball B was thrown. So actually, the time t for ball B should not be t. So if you made that mistake, you don't get the answer, right? The time t for ball B is actually t minus 2 because it was thrown 2 seconds later and then it strikes the ground at the same time with ball A. So don't make that mistake. If you make that mistake, then you don't get the answer. I'm sure somebody did make that mistake. And then plus a half acceleration minus 9.8, right? So here we are also going to have t minus 2 squared. This is because it was thrown 2 seconds after ball A was thrown. So delta y is going to be minus 5.5 t plus 10.8. Let me just verify because in the exam you will substitute 2 multiplied by 2 in the calculator because you don't want to make any mistake. So this is 10.8 and then minus 4.9 and then we have t minus 2 squared, right? So that is going to be t squared minus 4t plus 4. Yeah. If you don't see why that is the way it is, you probably got the question wrong either way. Okay, delta y will be equals to minus 5.4t plus 10.8 minus 4.9t squared. So 4.9 multiplied by 4. So this is plus 19.6t, right? And then what? Minus 4.9 multiplied by 4 again. So plus 19.6t. Is it plus? No, it is minus, because we have minus multiplied by plus. So we have minus. So let's just verify here, because it seems like there's a lot going on. This is fine. This is fine. T squared minus 4t plus 4. This is fine. Minus 4t squared is fine. Plus 16t is fine. And then here we're supposed to have minus 19.6, not minus 19.6t. So, okay, that was another mistake. Yeah, it's always important to verify. So, delta y, so let's add the like terms. So, minus 5.4 plus 19.6, right? That gives me 14.2. So, we have 14.2t. And then 10.8 minus 19.6 minus 8.8. So minus 8.8, and then minus 4.9 t squared. It does not have a like term, so minus 4.9 t squared. So we can equate these two things, these and these. We can equate those because they are both equals to delta y. So 12t minus 4.9 t squared is equals to minus 4.9 t squared plus 14.2t minus 8.8. Okay, let me just verify. Yeah, this is fine. 12t minus 4.9t squared. Okay, that is fine. So obviously we have minus 4.9t squared plus 4.9t squared, right? So we can just drop that. So we're left with 12t is equals to 14.2t minus 8.8. Okay, so 12 minus 14.2, I'm getting 12 minus 14.2, I'm getting minus 2.2. So minus 2.2t is equals to minus 8.8. So t is equals to, so 8.8 divided by 2.2, I'm getting, what do I get? 8.8 divided by 2.2, I'm getting 4. So time t is 4 seconds. So this takes 4 seconds. Okay, there we go. That is 3.1.1. It's a lot of work, to be honest. Yeah, 3.1.1. It's a lot of work. What about 3.1.2? We are looking for the value of z. So z is the height from which the two balls were projected, right? So we, how many marks? 3. Not sure it's worth 3 marks. Okay, but either way, delta y is equals to, we can take one between the two equations. Let's take 12t minus 4.9t squared, right? And then we know that t is equals to 4 when the two balls strike the ground. So when we substitute here, we shall get delta y, which is z. So 12 multiplied by 4 minus 4.9 multiplied by 4 squared is equals to, so 12 multiplied by 4 minus 4.9 multiplied by 4 squared. This is minus 30.4. So z is equals to 30.4, right? It is in meters, right? But z is just going to be 30.4. Yeah, because the meters is here in position, right, on the brackets there. But yeah, the two balls are projected 30.4 meters above the ground. Okay, what about 3.1.3? We are looking for the value of y. So y is the maximum height reached by a, right? So if I still remember a, the initial velocity is 12, the acceleration is minus 9.8. Maximum height, we know that vf is equals to 0, right? And then we are looking for delta y, right? So let's do that. Vf squared is equals to vi squared plus 2a delta y. So we have 0 squared being equals to 12 squared plus 2 minus 9.8 delta y. So delta y is equals to minus 12 squared divided by minus, well, 2 multiplied by minus 9.8, right? So delta y is equals to, so 12 squared divided by 19.6. This is 7.35 meters, right? But y is not going to be 7.35 meters, right? Y is going to be equals to 30.4 plus 7.35. I know we just lost some people there. I know somebody didn't add the two numbers. So y is equals to 37.75 meters. So there we go. That is the value of y. And then 3.2, we are supposed to, on the same set of axes, sketch the velocity time graphs for ball A and B while they're in free fall. Okay, so let's do that. Well, let's have our axis first, right? That's V, that's T. So T in seconds, V in meters per second. So the initial velocity of ball B is 12. So 12, I'm taking up as positive. And that of B is minus 5.4, right? We know that the time T here, we can just put it as T, but we know fully well that it is 4 seconds. Okay. And then the second ball is projected 2 seconds after, right? B is projected 2 seconds after. So here we have ball A. Ball A starts there. And then ball B will start somewhere here, which is 2 seconds after. So what happens to ball A? Ball A reaches maximum height after some time. And then it goes on to strike the ground at time T. Yeah, which is somewhere there. And then what? Let me just draw a straight line here. On the same set of axes. Okay, the question says sketch, so I wanted to ask if you had a graph paper, but I don't think you had. Okay, so I'm putting those dotted lines there so that I can be